In this video, we're going to derive what's called a hedonic wage function, which is the relationship between the wages firms have to pay and the risk of injury on the job and the work uh, places they provide. In the scenario we're going to present, we're going to have two firms. One provides a relatively safe working environment. The other provides less safe working environment. In this model, we're going to model two different kinds of employees. One group is risk averse, and the other is more willing to take a risk, right? So as firms invest in reducing injury probabilities within a specific work environment, they encounter a trade-off when attracting workers. This trade-off is illustrated by the blue isopropic curve in the graph below, which I have over on the right here. I have two copies of this webpage. This curve shows how that firms can offer high pay with high risk or offer low pay with low risk. And we're holding profit and other work conditions constant as we do that, right? So let's do a little exploration here. Let's look at the first type of firms. The first type of firms are firms that are offering relatively safe work environments, right? At point A, firm X right here offers a risk of 3.2. And this is, the risk here is maybe an index from 0 to 100, right? 0 being the lowest risk, 100 being the highest risk, maximum risk. And so we converted it into an index, right? That's pretty common, especially in government data, right? So the risk is 3.2 at point A, right? And the salary is 56. Okay, now sliding up this isoprofit curve, we're holding profits constant. We're allowing the wage to increase, and we're allowing risk to increase. Every other factor is being held constant. And the firm can keep profits constant if it increases risk from 3.2 to 10, right? And increases the salary, the annual salary from 56,000 to 6.8 thousand per year, right? So the risk level is 10, the salary is 60.8. Now at point C, profit is still being held constant, right? We have even more risk of injury, and we also have a higher salary, the risk level being 16.8 and the salary being $62,800, right? We hit enter, we can check our work, right? Now, when we hit enter, the graph is changed, right? It adds an indifference curve or an isoprofit curve below the one here, right? This one is the middle isoprofit over here, right? And so it adds an isoprofit that's below this one and adds one that's above it, right? Point A moves from here up this isoprofit, and then it jumps to this isoprofit. Point C moves down this isoprofit and then jumps down to this isoprofit. Because what we want to do is we want to see what happens to profit and wages if we hold risk constant, right? So we're going to hold risk constant at 10, and we're going to see how wages and profits change. Now, because I'm going to scroll this up, right? I need to reset. I need to reload this web page. We have a new point A and a new point C, right? Risk is being held constant at 10. So we're holding constant risk at 10. At point A, paying an annual salary of $62.1 thousand yields a firm an economic profit. So we have to go up the isoprofit to find. So anywhere on this curve, right, on this highest curve, profits are being held constant at negative 1.115, right? Jump down to B. Notice the risk is still the same, 10. The profit increases to 0, from this negative value to 0, because wages went from 62.1, they dropped to $60.8 thousand, right? So at point B, the annual salary is 60.8 thousand. At that salary, firm X yields an economic profit of $0 million, right? And then from point B to point C, we're dropping the salary even further. We're holding risk constant at 10 and a lot of other factors constant, every other factor constant. We're just dropping the wage. And when we drop that wage from 60.8 to 59.5, profits bump up to 1.21, right? So paying an annual salary of 59.5 yields the firm X an economic profit of 1.21. Now, when I press enter, what happens? Okay, so this is what it was before I pressed enter, and this is what it is after I pressed enter, right? Point A moves down this isoprofit curve to there. Point C moves up this isoprofit to there, right? So now we're going to hold the annual salary constant. We're going to hold the annual salary constant to see how risk affects profit, right? So in order to reset the diagram, again, I have to hit the reset button here, right? Reload the website. Then I'm hit resume. Okay, at the new set of points, A, B, and C, well, B is still the original point, right? This hasn't changed, right? B hasn't changed, but A and C have changed, right? The annual salary firm X pays is being held constant at 60.8. At point A, firm X economic profit, we slide up, is, negative 1.15, right? And its work environment has a risk level of 8, right? Now, if we increase the risk level from 8 to 10, we're now at point B because we're holding salary constant at $60.8 thousand. Profit drops to 0, right? At point B, firm X's profit is 0. And its work environment has a risk level of 10, right? Now, point C, when we jump to point C, risk has jumped to 13, from 10 to 13, right? Economic profit increases to 1.21. Now, pressing enter draws firm Y's isoprofit curve. Now, notice firm Y generally has higher risk than firm X, right? Firm X has relatively low risk. Firm Y has relatively more risk, right? And we have a single isoprofit here. All right, so now I got to reset this graph so it looks like this one over here. Now, the red isoprofit curve models a trade-off a firm with a risky work environment, battleship, for example, is faced with. At point A, firm Y offers a risk level of 19 and a salary of 63.9. Moving up the isoprofit, we're holding profits constant, right? But risk of injuries going up to 25.8. And in order to hold profits constant, we have to raise the wage up, and we raise it up just to the point where profits remain 0, right? Because this is going to be the isoprofit that corresponds to 0 profit, right? So now the firm offers a risk of 25.8 and a salary of 68.7, right? Then, if we move further up the isoprofit, in order to keep profits at 0 with a work environment risk of 32.6, the firm has to increase the salary to $70.7 thousand per year, right? Now, when we hit enter here, we're going to get isoprofit above and below this isoprofit, right? So now, for this higher risk firm, we're going to hold the risk of injury constant at 25.8, and we're going to let the salary go from 67.4 up to 68.7. which was the value at point B here, and then to 70 to see what happens to profit, right? So let me reset this graph. At the new set of points, A, B, and C, remember B is not really new. A and C are new, right? Risk is being held constant at 25.8. At point A, paying an annual salary of $70,000 yields firm Y an economic profit of negative 1.15, right? Now, if we move down to point B, profit increases to 0 because the salary falls from $70,000 to $68,700, right? So point B, paying a salary of 68.7, holding everything else constant, including risk at 25.8, increases the firm's profit to 0, right? Further lowering the wage to 67.4 per $1,000 per year can increase the profit to 1.21. What does pressing enter do here? It moves point A down this isoprofit curve to here. It moves point C up this isoprofit curve to here, right? So we can hold annual salary constant, right? We want to hold annual salary constant and see what happens when we increase the risk. What happens when we increase the risk? What happens to profit when we increase that risk, right? So again, to reload this, I'm gonna reload that, and then I'm gonna hit resume. Now at the new set of points A, B, and C, the annual salary firm Y pays is being held constant at 68.7, right? $1,000. At firm A, risk is 24. And that results in a profit of negative 1.15, right? Okay, so now we're going to jump from point A to point B. We're holding the annual salary constant at 68.7. Risk goes from 24 to 25.8, right? So risk jumps to 25.8. And that results in economic profit of 0, right? If we jump to point C, the risk level has increased to 29. We're holding constant the income, the annual salary, $68,700. We're holding that constant from A to B to C, but we're allowing the risk to rise to 29, which results in a 1.21 economic profit. Now, when we press enter here, we get something different. We get risk-averse workers indifference curves, right? So let me reset this over here. This worker here, the green worker, happens to be a risk-averse worker. They tend to prefer less risk, right? Workers, whether they're risk-averse or risk-taking, generally opt for safety workplaces unless higher compensation is offered by those with riskier environments. As the risk falls or pay increases, worker utility increases. So as we move up the indifference curve, worker utility is held constant. So at point A, worker N is the green one here, is willing to accept a risk of 33.2 if paid $58,800 per year. If the employer offers a risk environment of 10, the worker would be indifferent between 3.2 and 10 if the pay goes from 58.8 up to 60.8, right? So the worker is indifferent between points A and B, right? Because although the risks are higher, so too is the pay, right? At point C, the risk is 16.8. The salary is 65.6, right? Worker utility is the same. Worker utility is the same at point C as it is at B. The worker is just as happy with C as B because although there's more risk, there's a huge increase in pay. So that increase in pay compensates this person for the risk they're taking on, right? So we'll press enter here. And notice what happens to our graph when we press enter. We get an indifference curve above this one, and we get an indifference curve below this one. Point A moves to here. Point C moves to here, right? So that we can see what happens to utility as the salary is increased, right? So let me reset this over here so we can answer the questions that follow. At points A, B, and C, risk is being held constant, again at 10, right? At point A, worker N, the green worker, receives 436 units of utility from that level of risk, 10, and a salary of 62.1. So with this salary and that risk, the worker derives 436 units of utility from it, right? At point B, the salary is reduced to 60.8. The risk is held constant at 10, and the worker derives 400 units of utility. At point C, salary goes down further, right, to 59.5. Risk is being held constant at 10. That worker derives 329 units of utility from that. Okay, notice what happens to our points here when we pressed submit, right? When we click submit. Point A moves down to here. Point C moves up here along this indifference curve, right? So let's refresh that so we have the same diagram. At the new points, A, B, and C, worker N's salary is being held constant at 60.8, right? Salary is being held constant at 60.8. Risk is allowed to increase from 7 to 10 to 12, right? At point A, worker N's utility is 436. So it drives 436 units of utility from being paid $60.80 and accepting a risk level of 7. At point B, salary is being held constant at 60.8, but risk is now 10, right? And that reduces this person's utility to 400. At point C, risk is further increased to 12, while salary is held constant at 60.8. And at point C, with a risk level of 12 and a salary of 68.8, the worker derives 329 units from that, right? Okay, pressing enter generates the risk-taking worker, right? So let's refresh this to get our risk-taking worker here, right? Okay, while the green indifference curves reflect the risk and pay preferences of risk-averse workers, the orange curve depicts the preferences of risk-taking workers for various combinations of risk and pay, right? At point A, worker M is willing to accept what level of risk? Well, 19, right? 19. If paid $66.7 thousand, right? The worker is indifferent between point A and point B. So moving to point B, the person's indifferent between these 2 points. Why? Well, although the risk of the job jumps to 25.8, the worker is compensated for that additional risk by being paid $68.7 thousand per year. Now, the worker is indifferent between point A and C because although the risk is now 32.6, this worker is getting a lot more money, right? Is being compensated for taking on that additional risk, right? $73.5 thousand per year. Now, when I press enter, I get an indifference curve above point B, and I get an indifference curve below point B. C moves to this indifference curve. A moves to that indifference curve, and we're holding risk constant 25.8, right? So let me refresh this. So I can answer the questions that follow. Okay, at points A, B, and C, risk is being held constant at 25.8, right? At point B, worker M receives, or sorry, at point A, worker A receives 744 units of utility, right? From a risk level of 25.8 and an annual salary of 70. Point B represents less utility, right? Why? Because the risk is staying the same, but the salary is only 68.7. So at a risk level of 25.8, an annual salary of $68.7 thousand, the worker derives only 716 units of utility. Okay, if the salary were further reduced to 67.4, at $67.4 thousand per year and at a risk level of 25.8, this worker derives a utility of 626. Okay, that does what to our indifference curves? It moves the points, right? It moves the points. A moves down this indifference curve to here. C moves up this indifference curve to there, right? So now we're going to hold the salary constant at 68.7 thousand per year, right? Now, point A, with salary at 68.7 and risk at 23, right? The worker derives 744 units of utility there, right? At point B, salary still 68.7, but risk increased to 25.8. That results in a utility level of 716, right? At point C, worker M's utility, right, is 626 at point C, right? Because they've taken on even more risk, but the salary is being held constant, 68.7. So 626 units of utility when the salary is 68.7 and the risk level is 28. As you might have seen, it reintroduces, it erases these indifference curves and redraws the ISO profits that correspond to zero profits, right? So this is firm X and this is firm Y. There's a lot more ISO profits here than these two, right? There's infinite many here and there's infinite many here, but we're only drawing the one where economic profits are zero. And why are we doing that? Well, if you remember, economic profits tend to be zero under competition, right? If your firm has a large economic profit, entrepreneurs are going to see that and they're going to jump into your market. and supply product in your market, which pulls down prices and reduces margins, right? Profit margins until you have zero economic profit, right? So since Firm X finds it easy to offer low risk work environment, cooks on a cruise ship, the risk of injury in its facilities is going to be 10, right? At this level of risk, it's going to offer 60.8 thousand dollars in pay, right? It's going to offer $60.8 thousand in pay. Okay, when it does that, it attracts a type N worker, right? The green workers are type N, right? Yeah. It types N type worker, right? Now, firm X would like to have a lower wage, right? That would result in a higher profit. That's what we learned, right? But would N type workers, would they want to be down here? No, because their utility is higher up here, right? This results in a lower utility for this worker. It results in a higher profit for this firm, right? The worker would love to be up here. This provides more utility for the worker, right? Because if we hold risk constant, right? If we hold risk constant, this light blue point is going to have more utility than the dark blue point because it's going to have a higher pay. However, firms don't want to go there because if a firm goes to point B here, right, its profit will be negative because its wages will be higher, right? So what happens is the N workers accept positions at firm X, and that occurs at this point A here. So let's refresh this over here. So as a result, worker N types are attracted to and accept offers at firm X. That's what it's saying here, right? All right, so firm Y, which, finds it more difficult to provide a low-risk work environment, example, cooks on a battleship. The risk of injury in its facilities is 25.8. At that level of risk, it can pay workers $68.7 thousand. Now, who's gonna accept those positions? Well, the type M's do, right? The workers who are willing to take on risk, they'll accept those positions. Why? Because they tend not to fear risk as much as risk averse workers, but also because this firm is paying them a lot more money than they would make at firm X, right? Let me extend this with a curve. If I extend this indifference curve, it's kind of hard to do with this pencil. For them to work, for these group of workers here to want to work at firm X would have to pay them this amount of money. Firm X would have to raise its salary offers to about $66, $66.0 thousand per year, right? Now, for this risk averse worker to want to work at firm Y, they have to be paid a substantially higher wage. So type N workers are fine working at firm X, and type M workers are fine working at firm Y. All right, so let me reload this here. And we'll continue answering the questions. Now, in the real world, we cannot observe indifference and isopropic curves. Instead, in this example, in our example, we observe the risk of injury. The risk of injury at firm X is 10. And we observe that firm X pays $60.8 thousand per year. That's all we observe at firm X. So we don't get to observe the indifference curves of the workers, and we don't get to observe the isoprofit of the firm. This is all we observe is point A, right? Then we also observe the risk level at firm Y is 25.8. And we get to observe the salary they're paying, 68.7. Again, we don't get to observe the ISO profit of firm Y or X. We don't get to observe the indifference curves of type M and type N workers, right? We only observe these 2 points. Let me refresh this right here. The line that is fitted to these points is called the hedonic wage function. The slope of the function is used to determine what a life's worth. It is equal to the compensating wage differential, right? This is the wage differential, 68.7 minus 60.9, right? Which is $7.9 thousand, right? So that's the first part of the slope of this function. So that's the rise, right? We're going to go up 70.9. So that's the rise. What is the run? The run is the difference between these risk levels, right? 25.8 and 10, which is 15.8, right? Now, what's the ratio of these two? What is 7.9 divided by 15.8? Well, I'm looking at this and I'm thinking if I multiply this by 2, I get 18, right? Carry the 1. I multiply this by 7, I get 14 plus 1 that was carried. I get 15.8. So it looks like 7.9 divided by 15.8 is 0.5, right? That draws in this line, right? And this line is the hedonic wage function. Now, since risk was assumed to be an index, we're going to translate it back to the probability of, say, fatal injury, right? If risk equal 10 corresponds to probability of death equal to 0.021, and risk of 25.8, if this corresponds to 0.022, right here, right? And this corresponds to 0.21, the compensating wage differential arises from the probability of a fatal injury exceeding that in firm X by 0.001, right? Thus, each of the workers at firm Y is going to give up $7.9 thousand to reduce the probability of fatal injury by in their job by 0.001. So essentially what we're doing is we're replacing this risk with 0.021, right? We're getting rid of the index and we're just changing them back to their original probabilities, right? And so if we do that, we got to recalculate the slope, right? So the slope is 7.9 is the rise, and the run is 0.001, the difference in these two blue numbers, right? Now, taking the ratio of these two values is what? We'll do the calculations in Desmos. I'm going to write that as $7,900, right? And then I'm going to divide that by this increase in the probability, 0.001. I changed this from $7.9 thousand with the word thousand to the number 7,900. And then I divided by this probability difference, right? The difference in the probabilities here, right? And I got 7.9 million, right? Because there's a comma and there's a comma. So this is 7.9 million, right? Which can be written with million in words as $7.9 million, right? Now this $7.9 million, this is the amount that 1,000 workers, right? This is 1 in 1,000 workers, right? So if we have 1,000 workers, translates to 1 in 1,000 will be killed on the job, right? 1 in 1,000. So if we just assume that there are 1,000 workers at firm Y, so $7.9 million is the amount that 1,000 workers at firm Y would collectively give up to save one worker's life during the upcoming year. So this is how they calculate the value of life. And the value of life at firm Y is $7.9 million.